Hi, good morning. Today we are going to discuss about double annihilator. In the last class we have discussed about double dual. Okay. Now what do you mean by a double annihilator? So we have already discussed V is isomorphic to V double star and the map is phi from V to V double star defined by phi of alpha equal to L alpha, and we have proved this phi is 1 to 1 on to also it is a linear transformation. That means phi is an isomorphism and the map is L alpha. And L alpha is defined as L alpha from V star to F. It is a linear functional on V star. Therefore, L alpha of F is equal to F of alpha. Okay. Now let W be a subspace of V. Then W naught is equal to set of all F belongs to V star such that F of alpha equal to 0 for every alpha belongs to W. This is our definition of uh, W naught. Okay. So this is our definition. Now, what is W double naught? Double annihilator. This from W naught, that means F belongs to V star. Now, W double naught is equal to set of all L belongs to V double star. Set of here F belongs to V star. Here set of all L belongs to V double star. Okay, such that f of L of f equal to 0 for every f belongs to W naught. L of f equal to 0 for every f belongs to W naught. Clear the definition? W double naught is equal to L belongs to V double star such that L of f equal to 0 for every f belongs to W. This is the definition of L double naught. Sorry, W double naught. Now we are going to prove one result. Prove that W is a subset of W double naught. So how this possible? Actually, W double naught is set of all L belongs to V double star. Okay. But these are linear functionals. And W is a subspace of V. And here we are going to prove W is a subset of W double naught. Here elements are alpha and here linear function. Then how this possible? Here actually we are doing, this is an identification actually. We are identifying that W is a subset of W double dot. Okay. You see, there is an identification like that. If we have a null belongs to V double star by our theorem, I think 17, there exists a alpha belongs to V such that phi alpha equal to L alpha, which is equal to L. Or there exists a unique alpha belongs to V such that phi alpha equal to L. We have that result. So here we are identifying this V double star with V. Okay, similarly, now moving to proof double naught W double naught is equal to this one, and which is same as for every alpha, for every L belongs to V double star, there exists a alpha belongs to V such that L is equal to L alpha. Okay, therefore this is equal to set of all L alpha belongs to V double star such that L alpha of F equal to 0. That is 0 equal to L alpha of F, and by definition this is equal to F of alpha for every F belongs to V naught. Sorry, W naught. So here this is equal to for every alpha belongs to V double star, there exists a alpha belongs. So we are identifying. This is actually not equal. This is actually identification. Okay. But still we are writing equal to. This is actually an identification. So we are identifying W double naught as subset of as this subset. That is set of all alpha belongs to V such that F of alpha equal to 0 for every F belongs to W naught. Okay, therefore we can identify W double naught with a set of all alpha belongs to V such that F of alpha equal to 0 for every F belongs to W naught. Okay, now let alpha belongs to W. We have to prove W is a subset of W double naught. Let alpha belongs to W. Then for all F belongs to W naught, F of alpha equal to 0. And second, let alpha belongs to W. Then for all F belongs to W naught, F of alpha equal to 0, because we are considering W naught as set of all F belongs to V star such that F of alpha equal to 0 for every alpha belongs to W. So if you take one member from this set, then for that F of alpha equal to 0 for every alpha belongs to W. Okay. Therefore, if you then for all F belongs to W naught, F of alpha equal to 0. Therefore, alpha belongs to uh, alpha belongs to W double naught. Because what is the definition of W naught? Double naught. Set of all alpha belongs to be such that F of alpha equal to 0 for every F belongs to W naught. Okay, therefore alpha belongs to W naught. This implies W is a subset of W double naught. Okay. Now moving to one theorem. If S is any subset of a finite dimensional vector space V, then S naught naught is the subspace spanned by S. That is S double naught is equal to, we have to prove S double naught is equal to subspace spanned by S. That is span of S. Okay. Now we are assuming let W be the subspace spanned by S. Then clearly W naught is equal to S naught. Okay. So we'll check how we get W naught is equal to S naught. We have W is the intersection of all subspaces of V containing S. W is the intersection of all subspaces of V containing S. Therefore, S is every subspace of V containing S, and we are considering intersection of all subspaces of V containing S. So clearly S is contained in W. Okay, therefore by our previous result W naught is a subset of S naught. Now we have to prove the converse. Okay, we have this result. Now we have to prove S naught is a subset of W naught. So for this you take some F belongs to S naught. This implies F of alpha equal to 0 for every alpha belongs to S. Okay, so if you take any beta belongs to W, you can write as beta is equal to C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n. Okay, where alpha 1, alpha 2, etc. alpha I belongs to S, because we are considering W is the span of S. Span of S. Span of S means linear combination of elements of S. So if beta belongs to W, then beta you can write as C1 alpha 1 plus etc. plus Cn alpha. Now what is f of beta? F of beta equal to this one, and that's equal to f1 of alpha 1 plus C2 f of alpha 2 plus etc. plus Cn f of alpha n. Okay, and which is equal to C1 into 0 plus C2 into 0 plus etc. plus Cn into 0, because we are considering let f, we are considering f belongs to S naught. That means f of alpha equals 0 for every alpha belongs to S. Okay, therefore alpha 1, alpha 2, etc. alpha n belongs to S. This implies f of alpha n equals 0, f of alpha 2 equals 0, etc. F of alpha n equals 0. Therefore f of beta equal to 0. Therefore if beta belongs to W, then f of beta equal to 0. As b is arbitrary, we get f of beta equal to 0 for every beta belongs to W. F of beta equal to 0 for every beta belongs to W. This implies f belongs to W naught. So we are taking f belongs to S naught, and here we get f belongs to W naught. Therefore, S naught is a subset of W naught. Already we get W naught is a subset of S naught. Therefore, S naught is a subset of W naught implies S naught equal to W naught. Now why we are proving this? We have to prove S double naught is equal to W. So S double naught or double annihilator of S equal to W implies, and if we prove W equal to W double naught, then what we get? S double naught equal to W double naught, which is equal to W. Okay, as proof, and we can easily prove. Okay, now we have one theorem. Uh, we have S naught. What we get? We have S naught is equal to W naught. What we have to prove? We have to prove S naught is equal to span of S. Okay, and span of S is W. That is, we have to prove S double naught is equal to W. This is what we have to prove. But we have S naught is equal to W naught. W1 equal to W2 implies W1 naught is equal to W2 naught. That we have already discussed in the last class. Therefore, S double naught is equal to W double naught. So to prove this S double naught is equal to W, we have to prove W double naught is equal to W. Okay, already we get W is a subset of W double naught. Now from this dimension rank, sorry, we have this theorem 16, dimension of W plus dimension of W naught equal to dimension of V. Okay, and same apply this theorem for W naught. Dimension of W naught plus dimension of W double naught is equal to dimension of V star. Here W is a subspace of V and here W naught is a subspace of V star. Okay. Therefore, as dimension of V equal to dimension of V star, we get this one. And from 1 and 2, if you compare this, we get dimension of W is equal to dimension of W double naught. W is a subset of W double naught and which satisfies the condition dimension of W equal to dimension of W double naught, and that implies W equal to W double naught. Okay, therefore S double naught is equal to W double naught, which is equal to W. Therefore S double naught is equal to span of S. Okay, that's all for this session.